The world of technology just experienced a seismic shock, a moment that will be remembered for years to come. News from China has sent ripples across the globe, capturing the attention of scientists, engineers, and everyday people alike. A breakthrough has been announced that could change everything we know about electronics, sending shockwaves through the tech industry and beyond. For decades, silicon has been the undisputed king of the digital age, powering every smartphone, laptop, and server. It's the invisible backbone of our modern world, quietly enabling the devices we rely on every single day. But today, that foundation has a major crack, a disruption that could upend the very core of how our technology works. Chinese scientists have created a functional computer chip that does not use silicon at all. Instead, they've harnessed new materials and innovative designs to achieve what many thought was impossible. This is not just a small step forward, it's a giant leap into a new technological frontier, one that could redefine the limits of computing power and efficiency. The devices you use every day, your phone, your computer, even your smart home gadgets, might soon be based on technology that is fundamentally different from anything that came before. Imagine electronics that are not only faster and more powerful, but also incredibly energy efficient, lasting longer on a single charge and generating less heat. This is the promise of the new non-silicon chip, a revolution that could touch every aspect of our digital lives. The news comes from Shanghai, where a pioneering company has moved beyond theory and actually produced these chips at scale, turning science fiction into reality. This isn't just a lab experiment anymore. It's the start of a real industrial shift, with factories gearing up to manufacture the next generation of processors. For years, experts warned we were hitting the physical limits of silicon. The race to shrink transistors and pack more power into smaller spaces was reaching a dead end. Now, a door has opened to a new path, a future where innovation is no longer constrained by the old rules. This non-silicon chip offers a way around those limits, allowing for smaller, more efficient transistors and unlocking new possibilities for device design and performance. The race for the future of computing has just been dramatically altered. Companies and countries around the world are now scrambling to catch up, eager to be part of this new era. We are standing at a pivotal moment in history, similar to the transition from vacuum tubes to transistors, a leap that once seemed unimaginable, but changed everything. The world has depended on silicon for over half a century, building an entire digital civilization on its remarkable properties. Now, for the first time, a viable alternative is stepping into the light. The dawn of a new era has arrived, and the future of technology will never be the same. To grasp the magnitude of this change, we must appreciate silicon's dominance. For over 70 years, this element has been the bedrock of modern electronics. Every microprocessor, memory chip, and integrated circuit is built on ultra-pure silicon. Its unique semiconductor properties, abundance, and affordability made it the perfect choice. Silicon's reign enabled mass production, making electronics accessible to billions. The entire global tech industry was built on the assumption that silicon would always be the primary ingredient. Software, hardware, and infrastructure are all optimized for silicon chips. This is why a viable non-silicon alternative is so revolutionary. It challenges the entire paradigm that has governed our digital existence. The digital age's progress was fueled by Moore's law. In 1965, Gordon Moore predicted that the number of transistors on a chip would double every 2 years, slashing costs and boosting power. This became the industry's benchmark, driving relentless miniaturization. The result: computers shrank from room-sized machines to smartphones in our pockets. Each new chip generation brought exponential improvements. But in the last decade, Moore's law has slowed. The cost of developing new chips has skyrocketed. Engineers are now running up against the laws of physics. Components are just a few atoms thick, and silicon's reliability is breaking down. The era of easy gains is ending. The industry is desperate for what comes next. Shrinking chip features to the atomic scale brought new problems. Quantum tunneling lets electrons leak through transistor gates, wasting power and generating heat. This leakage worsens as transistors get smaller, making chips hot and requiring expensive cooling. That's why processor speeds plateaued and companies started adding more cores instead. Lithography, the process of etching circuits, has become incredibly complex and costly. Extreme ultraviolet machines cost over $200 million each. Only the wealthiest companies can afford to keep shrinking silicon. These physical and economic barriers created a silicon wall. Researchers have tried 3D stacking and other tricks, but these only delay the inevitable. To continue Moore's law, a new material is needed, one that works where silicon fails. The search for a successor is on. Enter molybdenum disulfide, or MOS2, a new champion among 2D materials. Unlike silicon's 3D structure, MOS2 can be a single atom thick. This thinness allows for transistors far smaller and more precisely controlled than silicon, solving the quantum tunneling problem. MOS2's ultra-thin channel gives superior control over electron flow, virtually eliminating leakage. The result chips that are both smaller and vastly more energy efficient. MOS2 also interacts with light in unique ways, opening doors to new sensors and optoelectronics. Its flexibility could enable bendable or transparent electronics. The challenge has always been mass-producing reliable MOS2 chips. Growing large, defect-free sheets was a major hurdle. Overcoming this is the key to turning MOS2 from a lab curiosity into a world-changing technology. By 2000, Shanghai Atomic Technology Inc., or SATE, is at the center of this remarkable technological breakthrough, making headlines in the global semiconductor industry. SATE has pioneered a revolutionary method to produce 4-inch wafers that are uniformly covered in high-quality, single-layer molybdenum disulfide, or MOS2. This material is known for its exceptional electrical properties, and producing it at this scale is a significant leap forward for next-generation electronics. This achievement marks a critical milestone for the industry. Scalable manufacturing is the essential first step toward making these advanced materials commercially viable. By automating the process, SATE is paving the way for mass production. But SATE's innovation doesn't stop at the material itself. They have perfected not just the synthesis of MOS2, but also the entire process required to transform it into fully functional semiconductor circuits, ready for real-world applications. Their integrated circuits now contain thousands of MOS2 transistors, each one a testament to the precision and reliability of their process. This is a monumental proof of concept, demonstrating that 2D materials can be used to build complex, high-performance chips. Even more impressive, SATE has achieved high yield rates, meaning that the vast majority of chips on each wafer are fully functional. This dramatically improves the economics of production, making it feasible to bring these chips to market. SATE's team has focused on optimizing the entire production chain, tackling and solving a wide range of practical engineering challenges, from material growth to device integration. As a result, they have created the world's first foundry process specifically designed for 2D material-based chips, setting a new industry standard. This level of innovation didn't happen overnight. It's the culmination of years of focused investment, relentless research, and a clear, strategic vision for the future of electronics. SATE's strong industrial focus and commitment to practical solutions have set their work apart, capturing the attention of the world and positioning Shanghai as a new epicenter for semiconductor innovation. Why? The most immediate and striking impact of MOS2 chips is their incredible energy efficiency, which is set to transform the entire electronics industry as we know it. These ultra-thin transistors can switch on and off with almost no leakage, dramatically slashing power consumption compared to traditional silicon chips. This means devices can run cooler and use far less electricity, even under heavy workloads. For massive data centers, which currently consume vast amounts of energy and contribute significantly to global carbon emissions, MOS2 could lead to massive reductions in electricity use and a much smaller carbon footprint. Imagine entire server farms running more efficiently, saving millions in energy costs. For everyday consumers, this translates to longer battery life. Imagine a smartphone that easily lasts a week on a single charge, or laptops that can go days without needing to be plugged in. This is a game changer for mobile technology. With less heat generated, devices can be made smaller, lighter, and more comfortable to use. This opens the door to entirely new form factors, like ultra-lightweight AR glasses, compact wearables, or medical implants that last for years without replacement. MOS2's efficiency could spark a new explosion in computing power, allowing engineers to pack trillions of transistors onto a single chip. This means more powerful computers, smarter devices, and breakthroughs in processing speed. With this leap in performance, we could unlock true artificial intelligence, enabling machines to learn, reason, and interact in ways we've only dreamed of. Revolutionary scientific advances in fields like medicine, climate modeling, and robotics could become reality. MOS2's unique properties also enable new types of camera sensors with higher sensitivity and wearable health monitors that are more accurate and energy efficient, making technology more personal and responsive. At first, MOS2 will find its place in specialized high-performance applications, but as manufacturing techniques improve and costs drop, it could eventually challenge silicon in nearly every area of electronics. The benefits of MOS2 ripple through every aspect of technology, from the devices in our pockets to the infrastructure powering our cities. The future of technology is not just faster and stronger, it's also greener, more sustainable, and ready to power the next era of human innovation. This breakthrough lands in the middle of a global tech race. The US has imposed export controls to slow China's progress in advanced silicon chips. China's non-silicon chip pathway is a direct response, changing the race instead of catching up. If MOS2 chips succeed, export controls on silicon tools may become irrelevant. Researchers in the US and Europe have also led in 2D materials, but China has industrialized the technology first. China's state-driven focus on manufacturing gives it a strategic edge. This could shift the global technological balance, eroding decades of Western dominance. A new, independent supply chain for critical components is emerging. China could become a key technology supplier for the world. The geopolitical chessboard has a powerful new piece. Despite the excitement, silicon isn't disappearing overnight. The global infrastructure for silicon chips is massive and efficient. For many applications, silicon will remain the most cost-effective solution for years. But its absolute dominance is ending. We're entering an era of material diversification, using the right material for the right job. High-performance computing and mobile devices may adopt MOS2 first, while silicon remains the workhorse elsewhere. Hybrid chips combining silicon and 2D materials could emerge. This shift will drive innovation in materials, manufacturing, and design. Consumers will benefit from better products and new possibilities. The silicon era gave us the modern world. The multi-material era will define what comes next.